So I'll try to solve questions that you want me to solve. Last homework, so let's leave that to the second. So last homework, second question, we'll do it the second hour. So questions regarding the last homework, we'll do it the second hour after we collected all the homeworks. Any other questions? So everybody is good, in perfect shape? No problems at all? Everything's fine? Yep. Kakutani's fixed point theorem. Well, so we take a subset of a Euclidean space, an n-dimensional Euclidean space. Well, first of all, for it to be interesting, it has to be non-empty. Because we're going to define a function on it. It has to be compact and convex. Okay. So we take a non-empty compact convex set. Let F from S into S. So it's a mapping which takes, I'm sorry, not, well, I'll use the function notation, okay? So in function notation, it's a mapping from S to subsets of S, okay? Or a correspondence F from S to S. So when we say correspondence, actually what we mean is the image of every element in the domain is a subset of the range, okay? Be such that, okay, so what did we require for F to satisfy? B. So what did we require? Non-empty valued. Okay. So it's never maps it to the empty set. Non-empty. What else did we require? And convex valued. Okay. So if S and S prime, well, if T and T prime are elements of f of S for some S in the domain, then alpha T plus 1 minus alpha T prime is also an element of f of S. We want it to be convex valued. Okay, for every S, f of S is a convex set. Okay, be a convex valued function. Since we wrote it like that, I'm going to refer to it as a function that has a closed graph. Okay. Again, what do I mean by graph? Graph of F is the set of all ST in S square such that T is an element of f of S. Okay? So if this is the case, then there exists an S in capital S such that S is an element of f of S. We call this a fixed point of the function f, or the correspondence f. Okay? So there is an element whose there's an S such that the image of S contains itself. Okay? That's what Kakutani's fixed point theorem is. Okay? Simple illustration of that could be, for example, take S to be the interval 0, 1. Okay? So an unempty compact convex set. Okay. So F maps elements in this set to subsets of this set. Okay. What this says is that, okay, if f of s is non-empty and convex valued, okay, and has a closed graph, then its graph will have to cut the 45-degree line. Okay, that's a simple implication of Kakutani's fixed point theorem. Okay, so the theorem, we don't do the proof. By the way, Kakutani's fixed point theorem is stated in different ways. There's an alternative version which uses upper hemi-continuity, but we don't know what hemi-continuity is, so I prefer to use this version of the Kakutani's fixed point theorem. Okay, so that's what it is. Any questions about this? So we use this to prove the existence of a Nash solution. The correspondence, or the function that we used, was obtained by taking the Cartesian product of the best response correspondence of each agent. Okay. Any other questions? Any other questions?
Can we solve a question from homework 3?
Sure. Which one?
The second question.
Okay. So I did actually homework 3, second question. Okay. So I don't want to write the whole thing. So what I'll do is I'll put it up on the screen. So since I didn't prepare a PowerPoint a version of the homework for the screen, I'll use this. I don't want to write the whole thing. So this is the question you're talking about, right? So we have two agents who have rights over an indivisible object, okay? So me and my sister have a right over an indivisible object. Because the good is indivisible, only one of us can get it. So among us, we devise a method to allocate this object, okay? So if I get the object, my sister will feel bad. If my sister gets the object, it would be unfair to me. I would feel bad. So what we do is we use a mechanism to decide on who gets the object and how much he pays the side who doesn't get the object in compensation. So each of us submit a sealed bid. The highest bidder gets the object and pays the other agent the average of the two bids. Well, if me and my sister bid, if player one and player two bid the same amount, then there is no the highest bidder. There's two highest bidders. So in that case, normally we would flip a coin. But again, at that stage, I didn't want to introduce randomness. Take a look at what happens if we flip a coin. Okay, so in that case, agent one gets the object and pays agent two. Well, the average of the two bids is the same. If we bid the same amount, pays the amount that agent two bid. Okay, so we're going to analyze this. If we played this game, how much would or should each agent bid, and what would happen at the end of the game? But in order to take care of that, we first have to model the situation. So again, when you're modeling the situation, the first decision that you have to make is, do you want to model as a four-tuple, quadruple, or three-tuple? Okay. Again, for us, the three-tuple is actually the most useful one. So unless otherwise specified, I would like to model it in this form, Ri, or its numerical representation. Okay. So, but again, since each agent submits a sealed bid, it's as if they take an action simultaneously. That's why we can model the situation in this form. Okay. So the first step is easy. There's only two players. We'll denote them with play 1 and 2. The next step is the strategy set of each agent. Well, what do they bid? Decide on how much money. Each agent submits the highest bid. So they bid a number. They write a number on a piece of paper. So we can say that it's any number from 0 to infinity. Okay. Where SI in capital SI denotes the amount that agent I bid. Okay. Always explain what these mathematical objects corresponds to. Okay. So these were the easy steps. Now we have to write the numerical representation. Okay. Now we have to write the numerical representation of the preferences. Now, at this stage, it's usually a good idea to think about outcomes. Even though we don't use it in our model, it's a good idea to think about the outcome. Now, what is an outcome here? Well, there are many ways to model an outcome, but in this case, I think the most intuitive, trivial way is a pair. So there's two pieces of information. Who gets the object? How much he or she pays. Okay? So that's an outcome should consist of a pair, which denotes who gets the object and how much he or she pays. Okay? And each agent cares about, well, in this case, I haven't written it down. I should have. I haven't written down, but from the auction games, it should be familiar. I should have said each agent cares about net gain, okay, how much they get. So let's write S1 for any S1, S2 in capital S. U1, S1, S2. Well, again, we said there's two. Who gets the object, how much he pays. So under what condition does agent 1 get the object? If his bid is at least as much as the bid of the second agent. So that's if S1 is greater or equal to S2. Agent 1 gets the object. Because he values it at V1, it's as if he has earned V1 liras, but then he has to make a payment. How much does he pay? He pays the average of S1 and S2. So that's a loss. So his net gain is this much. Okay, yep.
Yeah, but I think we should separate the equality case, because in that case, he doesn't pay the average, but he just pays his bid.
Okay, well, if S1 is equal to S2, then it will be the same thing. But yes, it's, if the story was different, so if S1 is equal to S2, the average of S1 and S1 is going to be, or S2 and S2 is going to be equal to S2, okay? So if he doesn't get the object, that is, when does he fail to get the object? If his bid is less than the bid of the second agent, then he is paid by agent 2 gets the object, and he's paid the average of the two bids. So that's S1 plus S2 over 2. Okay. And then for agent 2, we do the same idea. If agent 1 gets the object, Then agent 1 pays him this amount, the average of the 2 bids. If agent 1 doesn't get the object, it's agent 2 gets the object, which means that it's as if he earns V2 liras, but then has to make a payment of S1 plus S2 over 2 to the other agent. So his net gain is V2 minus S1 plus S2 over 2. That's it. Okay? So the modeling part is done. Find the best response correspondence of the agents. So what do you do for this? Sir? We take S2 constant and maximize, find the maximizers of the function if it exists. Okay? Well, taking derivatives would not be that useful here. First of all, the function has a discontinuity for almost all values of S1 and S2. So in these cases, I strongly recommend that you take a raw picture, okay? But of course, you know, it's not possible to draw a picture in every case, okay? In those cases, you have to use optimization. So it's a standard optimization problem, maximizing a function over a constraint set. The constraint set is S1, okay? Capital S1, non-negative real numbers. So you're doing a standard optimization problem, but when you're doing it, just be careful, okay? Taking derivatives and equating to 0 doesn't always give you the maximum. Sometimes the maximum doesn't exist. Sometimes the function is not differentiable. Sometimes the maximum is on the boundary, okay? So you have to be careful. But again, always trying to draw a picture is a good idea. So to find the best response of player 1 for any S2, for any given S2, we're looking for the maximizers of U1 as a function of S1 given S2. So we'll draw the picture of that. So S2 is given. So let's mark S2 here. Why am I marking it? Because the function changes behavior when S1 is bigger than S2 and when S1 is less than S2. That's why I marked S2. So if S1 is less than S2, that's a simple linear function of S1. It's a line with slope 1 over 2. And when S1 is equal to 0, it's S2 over 2. So it's something which starts from here, S2 over 2, and is increasing. Goes up all the way to up to this point. That's not included. And at that point, if that point was included, the value would be S2 plus S2 over 2. So that point would be S2. Okay. Now pass S2. That's the behavior of the function. That's again linear in S1. So it's again a line. Actually, it has a slope minus 1 over 2. So I'm going to draw a line with slope minus 1 over 2. And where does that line start? Okay. So if I let S1 equals to S2, that's V1 minus S2. So the question is, where does V1 minus S2 lie? Does it lie? Is it at this point in this region? Is it equal to S2? Is it less than S2? Which means that maybe we should have more than one picture because all of them are possible. So we could have a picture like this. By the way, this point is V1 minus S2. It could be like this, okay, or could be like this. Okay. So this is the case where V1 minus S2 is equal to S2, or S2 is equal to V1 over 2. This is the case where V1 minus S2 is bigger than S2. Okay. Or S2 is less than V1 over 2. And this is the case where V1 minus S2 is less than S2, or S2 is bigger than V1 over 2. So the rest is just inspect the picture. The picture gives you the answer. By the way, I'll put this away. So next thing, we're going to find the Nash solution and then ask if the Nash solution is Pareto efficient or not. So let me use this side of the whiteboard. So for any S2 in capital S2, which is the set of non-negative numbers, B1 of S2 is equal to, again, from the picture, we see that we have several cases. Okay. So if it's the black case, the maximizer is S2. If it's the red, again, it's S2. If it's the green, there's no maximizer. Okay. So if S2, so it's the black or the red, if S2 is less than or equal to V1 over 2, if S2 is bigger than V1 over 2, there's no best response. That's it for player 1. Okay? And then we play the same game with player 2. Okay. So actually, let me use this picture again. I'll make slight changes. Let me erase this part. So that's a function of S2. We're drawing U2 given S1 as a function of S2. So this time we have S1. So we're drawing it as a function of S2. So when S2 is less than S1, that is, we're to the left of S1, the function behaves like this. Just as before, that's a linear function with slope 1 over 2. So actually, I don't really care where it starts from, but where it ends up is the point where S2 is equal to S1. So it's going to be, this point is going to be S1. And then, again, we have several cases. By the way, okay. So this time, S2 can be equal to S1. So we have this point filled, but these points open. Okay. Again, what do? We look at, so what is the value of the function here? It's S2 is equal to S1. If S2 was equal to S1, this thing would be V2 minus S1. So this point is V2 minus S1. So the black situation is where V2 minus S1 is bigger than S1, or S1 is less than V2 over 2. The red case is where, I'll just go fast, S1 equal to V2 over 2. And the green is when S1 is bigger than V2 over 2. So we write the best response corresponds to player 1, player 2. Again, we have, so if S1 is less than V2 over 2, the best response is? There is none, right? So this function, the black function, doesn't have a maximizer. So that's when S1 is less than V2 over 2. There is no maximizer. If S1 is bigger than or equal to V2 over 2, then it's the red or the green. In both cases, S1 is a maximizer. Okay, that's it for the second point. So the third item asks, find the set of Nash equilibria of this game. Okay. Again, you can just use direct mathematical method. Okay. So, or use a graph. Okay. Which one do you prefer? Well, let's start with the graph. Pictures are very powerful tools, so try to make use of them as much as possible. Always label your pictures, label your axes, label everything that you use in your picture. So we have V1 over 2, V1, and then we were given V2 is less than V1, so V2 over 2. Let me draw the 45-degree line here. So V2 over 2, V1 over 2, V2, V1. So if S2 is less than V1 over 2, best response of player 1 is to play exactly what his opponent did. So for any strategy in this region, player 1 will play S2. And when S2 is bigger than V1 over 2, he doesn't have a best response. So that's the picture of B1. So let's draw the picture for B2. If S1 is less than V2 over 2, he doesn't have a best response. So for any strategy in this region, player 2 does not have a best response. For any strategy, for any S1 bigger than V2 over 2, his best response is to play the same strategy as player 1. So what we have here is that's included. By the way, this is also included. So that's this set. Okay? So far? So good? So the Nash equilibria is the set of all points corresponding to this region. By the way, you see, V2 maybe was less than V1 over 2. Okay? So when I draw the picture, there are many possible cases. This is only one instance of it. But once I draw it, all that matters is the relation between V1 over 2 and V2 over 2, not the relation between V1 over 2 and V2. Okay? So I don't draw the other pictures. Okay? So the set of Nash equilibria of this game, always write them properly. So Nash solutions, Nash equilibria, again, whenever we talk about a solution, we mean a profile. So it's a profile of strategies, S1, S2, in capital S, such that the first property is S1 is equal to S2. It's on the 45-degree line. And S1 is bigger or equal to V2 over 2. Hence, S2 is bigger or equal to V2 over 2, and less than or equal to V1 over 2. Okay? So far, so good? That's it. Any questions? So that's the set of Nash equilibria.
But if you did it mathematically.
Okay, so what if we did mathematically? So S1 star, S2 star is a Nash equilibria of the game if and only if S1 star is the best response of player 1 to S2 star. And S2 star is the best response of player 2 to S1 star. Okay? So when is this the case? So first, S1 star being a best response of player 1 to S2 star means that, first of all, the best response correspondence is non-empty valued. So this cannot be the case. So this set containing an element automatically implies that S2 star is less than or equal to V1 over 2. Okay? And so by this, we guarantee that this is non-empty valued. So S1 star should be an element of that set, but then it means that S1 star should be equal to S2 star. Okay? So this is implied by that. Okay? And the same thing, S2 star being an element of B2 of S1 star means that this set is non-empty valued, which means that this is the case, which means that S1 star is bigger or equal to V2 over 2. What am I saying? Greater or equal to V2 over 2. And again, so if S2 star is an element of this, S2 star is an element of a set with a single element. Well, if it's an element of a set with a single element, S2 star has to be equal to that element, which is S1 star. Okay? So those together implies S1 star equal to S2 star. That's common. And then they're all connected with an and is, oops. Okay, that's it. Okay? Any questions? So you don't always have to draw a picture, but pictures are powerful tools. It gives you insight, but when you're doing it mathematically, do it properly. Yep.
What if player 1 loses the game, his game is S1 plus S2?
Sorry, come again? What if player? I couldn't hear the exact thing. What if I'm sorry about that.
He lost the game, his game is S1 plus S2 over 2.
He lost the game. So what about that? What's the question?
Why it is like that?
Why it is like that? Okay, so it's about the modeling part. So if you remember, the story said the high bidder gets the object. If there's a single high bidder, the high bidder gets the object and pays the other agent the average of the two bids. So I bid S1, you bid S2. You lost, you bid less than, so S2 is less than S1. Okay? So how much do I pay you? S1 plus S2? Yes. Okay? So we all had equal rights of the object. So if I get the object, you'll feel bad. It will be unfair to you. If you get the object, it will be unfair to me. So if I get the object, I compensate you by giving you some money. If you get the object, you compensate me by giving me some money. The question is, how much? Well, this is one mechanism which says, okay, the payment should be the average of the two numbers. Okay? Any other questions?
There's a part D.
Oh, part D. Are the Nash solutions Pareto efficient? So, are the Nash solutions Pareto efficient? By the way, in this case, who gets at any Nash solution, who gets the object? Agent 1, which is good. Okay? The object goes to the agent who values it the most. Okay? So that's good in a way. Okay? That's something usually we desirable. So, are Nash solutions Pareto efficient? Yep. They are. Why?
Because we have two outcomes. But the two agents
Should be the same. Okay. So actually what your friend is using is one of the propositions that we stated in class. If you remember, if we said if S star maximizes summation ui of S, I in N, over capital S, then S star is Pareto efficient. Okay? So in this case, what is U1 of S1, S2 plus U2 of S1, S2? Well, if this is the case, it's this plus this, which gives us V1, right? If this is the case, it's this plus this, which gives you V2. So this is equal to V1 if S1, we said this is the case, S1 is greater or equal to S2. It's equal to V2 if S1 is less than S2. So what is the maximum value that this summation can take? As your friend suggested, it's V1. At the Nash equilibrium, what is U1 plus U2 equal to? Okay. At the Nash equilibrium, agent 1 gets the object. S1 star is equal to S2 star. So this is the case. So the Nash equilibrium maximizes the sum and hence is Pareto efficient automatically. That's what your friend has used. Okay. Another way to go could be, so we know that U1 of S1 star, S2 star is equal to V1 minus S1 star. Remember, S1 star is equal to S2 star at the Nash solution. Okay? At any Nash solution, S1 star is equal to S2 star. That's equal to this. So take another strategy profile. U1 of S1, S2. Okay? Well, let's also write U2 of S1 star, S2 star. And that will be S1 star again. Okay? Not again, that will be S1 star. So U1 of S1, S2. What are the possible values that this can take? Well, at this profile, agent 1 could be the winner of the auction. In that case, this is S1 minus S1 plus S2 divided by 2. Okay? And in that case, U2 is going to be, U2 S1 S2 is going to be S1 plus S2 over 2. Okay? So if S1 is bigger or equal to S2. So for S1, S2 to Pareto dominate S1 star, S2 star, this number should be bigger or equal to V1 minus S1 plus S2 over 2 should be bigger than V1 minus S1 star. But what does that imply? It implies that S1 star is bigger or equal to S1 plus S2 over 2. Okay? And actually, if this is bigger, this is also bigger. Right? The B1s cancels. But then what does that imply about this side? It implies that the direction of the inequality is reversed. So if one agent gains, the other agent loses. Of course, this is when, at any profile where agent 1 wins the auction. I should also consider the case where S1 is less than S2. Well, if S1 is less than S2, then U1 of S1, S2 is equal to S1 plus S2 over 2. And U2 of S1, S2 is V2 minus S1 plus S2 over 2. Okay? So this time, if, let's say, player 2, if player 2 becomes better off, it means that this number is bigger than this number, okay, which would imply, let me erase this part. Which would imply V2 minus S1 plus S2 over 2 bigger than S1 star, okay? So now I want to compare these two numbers. So that would imply that V2 minus S1 star is bigger than S1 plus S2 over 2, okay? But that is less than V1 minus S1 star. Remember, we assumed V1 is bigger than V2, okay? Which means that this number is bigger than this number. So if, when we move from S1 star to S2 star, if player 2 becomes better off, player 1 becomes worse off, okay? So that's a direct proof using the definition of Pareto efficiency. But what your friend suggested is a shorter way of doing it. So essentially, when you move from a Nash solution to any other profile, if you make player 1 better off, you're making player 2 worse off. Okay? Any questions? Any questions? Okay. Any other question that you would like to? Yep. So we're given ISO curves, indifference curves for both agents, one for agent 1 and for agent 2. We're asked to find, what were we asked to find? The best response correspondence of both agents, the set of dominant strategies of both agents, the Nash solutions of the game, and the set of Pareto efficient strategy profiles. Okay? So to find the best response of agent, the best response correspondence of agent 1, what we do is we draw horizontal lines. That is, we take a strategy of player 2 and ask on this horizontal line, what is the most preferred point for agent 1? Okay? So this point cannot be a most preferred point because when you look at the direction of the arrows, the direction of the arrows says that anything, so that's like an arc, anything inside the arc, anything to left, down, anything in this region is preferred by agent 1 to anything in this, on this indifference curve. So it means that all these points are preferred to this point. So this point cannot be a best response. So actually, as we move to the left, we see that we move to a point which is more preferred by agent 1. So if we keep doing this, we see that 0 is the best response of player 1 to this S2. But actually, that is the case for any S2. So just by looking at the picture, we see that B1 of S2 is equal to 0. So for player 1, this time we, for player 2 to find best responses of player 2, this time we draw vertical lines. That is, we say, given a strategy of player 1, okay, what is his best response? That is, which point on this vertical line is the most preferred point, is the most preferred strategy profile for player 1. This time we see that because of the direction of these arrows, we see that anything in this region is preferred to this point, and it keeps going out. So from this picture, we automatically observe that as we move up, agent 2 becomes better off. And this point is his most preferred point on that line, which corresponds to the strategy 1 of player 2. So from here, we see that B2 of S1 is equal to 1. So that was easy. Well, once you see that, we actually can conclude from here that player 1 has a strictly dominant strategy, and it is 0. Well, if 0 is a strictly dominant strategy, it's also a dominant strategy. The same thing here, okay? If, well, the same thing in the sense that player 2 has a strictly dominant strategy, and it is to play 1, okay? So that answers. So the next thing was the Nash solutions. Okay. Well, 0 is the best response to 1. 1 is the best response to 0. So the Nash solution is 0, 1. Actually, that's where the best response corresponds. The graphs of the, I was about to say that's where the best response correspondences intersect. The best response correspondences never intersect, but their graphs do intersect at the point 0, 1. Yes, sir, you had a question?
Can we find the best response of agents by writing its utility function?
Okay, well, you have to write a utility function, okay, which gives these isocurves. Okay, we know that there is more than, so for example, for player 1, you could have written S1 square plus S2 square multiplied by minus 1. Okay, so as long as it gives the same isocurve, that would work. Okay, but why do it when you have something simpler to do? Okay, but yes, it does work. So I haven't given you the function. Okay, I haven't told you what U1 is, so maybe this is not U1. But it doesn't matter. What matters for us is the preferences. Okay, so whether you use this preference relation or, I don't know, this one, okay, we still keep the minus, it yields the same isocurve, so it should yield the same best response correspondence. It would represent this function, and this function represents the same preference relation. And hence, they have the same best responses, they have, everything will be the same. Okay? So yes, you can use a function as long as it has the correct isocurves, but this is much simpler. And you write this, and then you, okay? Okay? So let me, so the Pareto efficient strategy profiles, that's actually the more interesting part. So for that, it's a good idea to actually draw the two families of indifference curves on a single graph. Because, so if I want to decide whether this point is Pareto efficient, I need to know what agent 1 thinks about this point. That's already in here. But also what agent 2 thinks about this point. So I have to draw an isocurve of player 2 through this point. And when I take this, cut it here, I have an indifference curve which goes like this. And the direction of the increasing preference is in this direction. So from this picture, I see that any point in this region, in the region bounded by this green curve, Pareto dominates this point. So this point cannot be Pareto efficient. Okay? So if I keep repeating, so the thing is, the green curve, okay, the green region, should be restricted to a single point, which is the point itself. Okay? So where do you get those things? When the isocurves are, when the indifference curves are tangent to each other. So take this point, draw the indifference curve of player 2. We already have the indifference curve of player 1. Okay. So for anything to Pareto dominate this point, it should make agent 1 it should make agent 1 at least as good as he was here. So to make agent 1 at least as good as he was here, we should pick a strategy profile in this region. But if we pick any strategy profile in this region, agent 2 becomes worse off. And this point is Pareto efficient. Actually, anything on the 45-degree line is Pareto efficient. Okay? But I would ask you to think about the same question. This time, the direction of the indifference curves, the direction of the normal vectors reversed. Okay. So agent 1 becomes better off as he moves away, as the profile moves away from the origin. Agent 2 becomes better off as we move away from the 1-1 strategy profile. Okay? Yep. Now let's give a break.
The set of highly efficient outcomes strategy profiles will be two axes from 0 to 1.
Will be the 2 axes. So let's think about it after the break. Let's talk about that. Let's take it. Sorry, I extended 3 minutes.